Okay, well it probably is. It seems to be more chelating the iron than actually reducing it. So it looks like it's still in like the 3 form by the looks of, if the colour is anything to go to with valency sort of thing. So I think I can't do it any better than that, fellas, really. Not in this short space of time, so I'm just going to load it up as you do. And it hasn't really thickened out like the copper does, so we're just going to put that in. Now, we're just going to see how that goes. Now, if this grows in the same, as I said, 3 or 4 days, but if it goes really dark red, then sort of that sort of molybdenum sort of red we're getting, and that sort of dark cherry red sort of thing. Well, then we're going to be getting closer to solving the copper conundrum, which is also part of the calcifuge conundrum, of course, because copper can be, housed, enclosed in chalk, of course, So, as I said, what is ash and why is it so alkaline? I keep asking Gideon and everyone else, no one seems to put up their hand because I don't think anyone's done the work. Hint, hint. But a friend and I, we were in the old chem club at school in my teenage years, and they were asking you to think about doing projects, and I think, well, I've always wondered what ash is. So we spent 3 weeks. Our hypothesis was it was going to be like an oxide or hydroxide or something because it's so alkaline and all that sort of thing, which it is. And we were totally shocked. We did this experiment. We couldn't believe it. So we did it a second week. Couldn't believe it. Everything came out the same. So we did it for the 3rd week. Third session of Chem Club, it used to be like, 2.5 hours sort of thing, doing these things, going through all the, sodium metal, all that sort of thing. All the cascade of things you do to try and work out what it is, and you're knocking these things off. It's not this, not that, blah, 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 blah. Hardly anything, this and there, and blah, blah, blah. And the 3rd week came out with the same results. So we, went to the, our lecturer, who was one of the greats of chemistry in this state, if not Australia at the time, and he made this famous statement to us, well, if that's what the science is telling you, that's what it is, That's what the result, all the tests are saying. That's what it is. You've done it, and you can't find you've made any errors anywhere, and you can't think of anything that could have gone wrong, and that you could retest or anything like that. And that's what it is. And I've gone through life for years and years and years, decades, with this knowledge at the back of my mind, what ash really is. And I think it's stood me in good stead because no one else would really believe it in the CP world. And it's such a conundrum. It's almost like saying, the highest micronutrient in peat is copper, yet CPs aren't supposed to like copper. It's that sort of, antithetical sort of a statement sort of thing, that sort of, as what was it, Einstein said that, that's where the science is. When you get one of these ballsed up sort of area where, everyone's known that that's the highest micronutrient, and you say CPs don't like bloody copper, there's something really majorly wrong with the general theory of the moment. There's something wrong there, and I think this is where we're going to crack through and find out what it is. Because I reckon, they always talk about pirates going to these areas over in North Carolina, and he used to pick up barrels of water because it used to stay potable for months at a time. They could go out for another 8, 9, 12 months with this water and still drink it, and it would be fresh. And they always talk about copper being so deadly to microorganisms, but they never say why. They said, it can almost instantaneously kill organisms. And I'm wondering, well, if it can take away iron like atoms away from things, and maybe pull them out of enzymes as well, denature enzymes in that way sort of thing, you're going to run out of oxygen. You're going to you're not going to be able to respire, and all plants also respire as well as photosynthesize. It's going to kill everything. It's going to kill cyanophyta. They're just going to starve anything that's well then, so that's the question, isn't it, fellas? If our organism likes a reductive flammable gas environment, why is it affected by copper? If the copper was taking away, well, maybe Maybe it's a bit like the nodules it likes a really strict anaerobic environment, and the reductive flammable gas only gets it so far. It needs the iron in order to suck out that last bit of oxygen. And of course, if the copper takes away the iron, it can't do that, it can't grow. I mean, that's another avenue or line of argument for why the organism is affected by copper. But then again, if that's true, we should be able to put iron back there in some form or fashion, maybe even as the ferrocyanide eventually. I don't know if I want to try that experiment, but you never know, we might do that eventually. But we'll see. Step one is to just find out whether the organism will grow and be redder, in quotes, in the egg. And then we'll try it again with eggy chalk, because we might find that the iron reacts slightly differently when it's also attached to the chalk, sort of thing. So we'll set this up properly. As I'll wait till those bubbles do dissipate in there. Let me get a screen. Oh, we are on spot colour and bugger. Always do that. Anyway, so we go back to normal. So what with the data coming back from this, squeezing it from one end, and data coming back from these things over time, we might be able to find out what it is that's in peat that causes the seeds to germinate, and we might be able to then bump it up. So not only do we actually have a non-peat medium that we can grow CPs in, but we can add to that some sort of eggy chalk with a few micronutrient elements there, but in the right way we can actually bump that up. So not only do they germinate seeds readily, they might almost germinate overnight. It's forced germination in a way, and we might be able to get pieces of leaves and stuff, and we force it to form a bud in like a week or something like that. You just put it in. Maybe if it's got copper there, it won't die, it won't rot off because of the copper there, but we've amended it with so much iron that the copper is not poison, or something like iron, like cerium or molybdenum or something like that, and we'll find out how to do it, sort of thing, and we'll get like a form of tissue culture where we're just taking small squares of Sarracenia leaves, sticking them on the surface, and you think they're just going to die and rot off because maybe there's so much copper there, but being balanced by some sort of acidophilic element like iron or molybdenum or something, cerium or something like that. They don't rot off, they stay there long enough, and maybe we drive them into producing buds in a week or 2 weeks' time. Almost guaranteed, 98, 99% strike rate, or something like this. So it would be like a pseudo form of tissue culture, and maybe we would want to transfer that for it from the so-called natural world, semi-natural world, from here out in the environment into a glass flask environment, and have like a tissue culture like arrangement. It's even more tightly controlled. So we get that 99 up to 99.99 strike rate or something in a flask. We lose one flask in 1,000. There's so much copper there, nothing else grows in it. Maybe there's some special thing with CP metabolism. They can handle the copper, other plants can't. So the only thing that grows in the jar is a CP or CP-related plants, because they have a particular metabolic process that they can handle it. They've evolved over millions of years to go out into these soils and be able to cope with these soils and therefore they can grow in the flask and nothing else can, and none of the other microorganisms. That's what gets me. They say that there's always microorganisms about. You always find one, and then I get blank jars. There's nothing growing in them. I'm thinking, well, pretty, but then again, it goes back to that fact, unless the organism there, it can't grow. It goes back to the reverse of extinction is forever. Once it's extinct, there is no organism. There's no, seed. There's no, capsule. To grow. If there's nothing there to grow, it can't grow, sort of thing. Nothing there in a dormant state, you can't. You can't germinate something that's not there, sort of thing. Extinction is forever, sort of thing. But anyway, this is a bit of a long chatty do. But I just think we're going to squeeze the problem now using the polystyrene, which is basically a way of sorting out things. We're going to squeeze it from both ends. Basically, the problem, as you said, there is some sort of problem with copper, but I don't think it's actually a problem. I think it's actually the answer is sitting there the answer to a bigger, brighter, better CP future is sitting there from the copper. If you can solve the copper, you can get to a new CP future, because it's definitely not the calcium, because the organism is actually growing there, and it doesn't seem to be impeded too much by the manganese. It's even, you can see it's even growing in there and starting to go green on the top there. I don't know if we can do that in the spot column there. You can actually go to spot column, we can go in there very slowly, get it to focus in there. You can actually see the organisms actually growing in there, in the bottle. You can see it, they're growing there, and it's also going green on the top there. So, you know, it's not affected by manganese. So the reductive protein will reduce the manganese down to the manganese dioxide, and there's a little bit of inhibition, but eventually it doesn't get in the way. So it really only leaves us with our two things, copper and iron, and I think there's a relationship between the two, and we're just going to solve for it, and that's where the real CP revolution comes from. Because we've taken peat out of the equation, we've taken sand out of the equation and found out there is a problem with the sand, which can be improved by using perlite, but is there iron in perlite? You know, it's so white and clear. Maybe there's some hidden iron in the perlite, because the original source material, the obsidian or volcanic glass, it's black, isn't it? So, you know, it's got something in it, I would say. Maybe it's got a lot of iron in it, and when you turn it into perlite, you don't realise that. Maybe that, and it's in a nice, safe, stable form. I don't know. And maybe that's what helped. Anyway, we can work on that over time. Okay, over and out for this somewhat rambling video. Okay, see ya.